Welcome back, learners. In the previous lecture, as you know, we have discussed about finding out the support reactions in the footing, right? So you have clearly known that we have calculated the support reactions in our project, and we have made them into the dead load, live load, and the combination of dead load and live load. Now, before we move on to the how to go with the design of the footing, first I have to understand that today let us learn about the design steps of the concentric loaded isolated footing. It means here there are two concepts. The first is I am teaching you about the design of the isolated footing, that is point number 1, that is on the one side. On the another side, along with the isolated footing, I am explaining you about concentrically loaded. It means your load from the column will be lying exactly at the center of the load of the footing. That means your column is exactly at the center of the footing. For example, if I want to explain, if I want to show concentrically loaded footing means, I can say like this. This is my footing, okay? So in order to show that it is center, I am just writing like this. So my footing is also, it is maintained exactly at the center like this, okay? So this is what we call it as concentrically loaded footing, okay? This is my concentric loaded footing. The column center as well as my footing center are going to match, right? So if it is an eccentrically loaded isolated footing means, so this will be like this, okay? So my footing center will be like this, whereas my column will present somewhere here like this, okay? It is not at the center. That is what we call it as eccentrically loaded isolated footing. Your center of the footing and the center of the columns are not matching. That time there will be a development of eccentricity, okay? So that we will see in the next lecture, okay? So usually we always try to design with the concentrically isolated footing only. So when there is an fouling of the footings, right, here what we are going to do for each and every column loading, so we will design the footing and we will take that footing dimension and we will make it on the column layout. When we do that, if there is any overlapping or the fouling of the footings, then we have to make some changes in the design. So somewhere which was concentrically loaded, we may make it into the eccentrically loaded. So when that there is an eccentrically loaded footing is required, so that time I will explain you how to design the eccentrically loaded isolated footing. So now as of now, first footing, let us go to the concentrically loaded isolated footing. Now before I explain this in my Excel sheet, so I have explained here that what is the design steps of the concentric loaded isolated footing. The first step is you are supposed to know the grade of concrete that you are going to use for the footing, right? So the grade of concrete for the footing will be usually considered same as that of the column, okay? The grade of concrete will be usually considered same as that of the column, okay? So first you should know the grade of concrete for the footing, which is represented by the symbol FCK, Okay, that is nothing but the characteristic strength of the concrete of the for the footing FCK. So that is the input value. It means we have to decide it. Okay, either it will not be calculated or it will not be obtained from the software. We have to give the input value. So therefore I have written input. Okay, that is the grade of concrete. So usually that will be given in the unit Newton per mm square. The grade of concrete will be given in the unit Newton per mm square. Okay, yes. So the next step is axial load on the column. This axial load on the column will be obtained from the software results. You can see here this f of y represents, f of z represents your axial load on the column. What about this f of x? What about this f of y? What about this mx, my, fz? So that we will see in the next lecture. But as of now, your axial load on the column will be obtained from the software for each and every column. Okay, that is column 53, 34, 36, 35, 20. So that value is nothing but your fz value. Okay, so for dead load is this one, so for live load is this one, and for dead load is this one. Okay, your fz value is nothing but your axial load on the column. Okay, your axial load on the column is your fz value from the software. That's why I have written this value will be obtained from the software, and we will consider that axial load in kilonewton. Okay, we will consider that in the kilonewton. So this is my second step, writing the axial load on the column. My third step is finding out the self weight of the footing. Okay, so finding out the self weight of the footing. So how will you find out the self weight of the footing? How will you find out the self weight of the footing? The self weight of the footing is usually considered as the 10% of the axial load of the column. Okay, the 10% of the axial load on the column. For example, if your axial load on the column is 1000 kilonewton, then the self weight of the footing will be 10% of the 1000. Okay, so 10% of the 1000, which will come 100 kilonewton. Okay, so that 100 kilonewton plus this axial load will give you the total self weight, that is 1100 kilonewton. Okay, if you are telling it in the form of kilonewton, then this will be 1100 kilonewton. That will be your self weight of the footing. Okay, the self weight of the footing is always taken in the form of 10% of the axial load of the column, right? If it is 1000, then 10% means 100. So therefore your self weight of the footing will be 100. Okay, the self weight of the footing will be taken as 100 kilonewton. So when I add up that self weight of the footing with the axial load, I will get the total load on the column. Okay, the total load on the column, and that total load on the column itself I have to use it, okay, for my design. The total load on the column itself I have to use it for my design. Okay, the total load on the column I have to use it for the design. Okay, so therefore you can see here that this is the axial load, this is the self weight in kilonewton. The total load that I have to design, for the design I have to use is axial load plus self weight, which will give you the total load in kilonewton. Okay, it will give you the total load in kilonewton, right? It will give you the total load in kilonewton, right? Okay, so what is the next step then? Right, so the next step is finding the moment at the base of the column. Okay, so this moment at the base of the column is also we are going to obtain from the software. That is nothing but your mx, my, mz, whether it may be dead load or live load, or your dead load plus live load, your mx, my, mz are your moment at the base of the column. Now which one I have to take for my design, that we will see in the next video. Okay, while explaining that with the help of your Excel sheet, I will tell you which one has to be considered for the design. But your moment at the base is those value which will be obtained from the software, which will be in kilonewton meter. Okay, that is moment at the base of the column. Then next you should know is the safe bearing capacity, that is SBC of the soil. Safe bearing capacity of the soil. Okay, your next step is finding out the safe bearing capacity of the soil. The safe bearing capacity of the soil is also, it is an input value. You will nowhere get it from the software or from any calculation. So by doing the plate load test in the site, you will get the safe bearing capacity of the soil, or by carrying out some other investigations on the soil at the site, you will get the safe bearing capacity of the soil, that we have to use it for our design. And that is an input value which will be given in kilonewton per meter square, which will be given in kilonewton per meter square. So once you know the safe bearing capacity of the soil and once you know the total load for the design, you are supposed to calculate the approximate area of the footing. You are supposed to calculate the approximate area of the footing. So how you calculate approximate area of the footing? It is nothing but your total load divided by the safe bearing capacity of the soil. Total load divided by safe bearing capacity of the soil. So when I do that, I will get the area of the footing in meter square. I will get the area of the footing in meter square. Okay, so that will give you the approximate area of the footing. Now usually, since my all columns whatever I have considered in this problem is of rectangular in nature, even my footing will also be, it will be in the rectangular in nature. And how we usually place the columns is that your longer dimension of the column will be parallel to the longer dimension of the footing. Shorter dimension of the column will be parallel to the shorter dimension of the footing. That means like this. This is the longer dimension of the column that will be placed in parallel to the longer dimension of the footing. This is the shorter dimension of the column and that will be placed in parallel with the shorter dimension of the footing. In case if I want to rotate the column, then what I will do, then again I will place in such a way that so they are going to be maintained in parallel only. They are going to be maintained in parallel only. Okay, that is like this, right? So like this, like this. So now here my column orientation is changed, but my shorter dimension of the column is parallel to the shorter dimension of the footing. Longer dimension of the column is parallel to the longer dimension of the footing. We always try to maintain that because that will make the footing more and more stable, and the calculations also it will make easier, right? So based on that, then definitely we have to do here rectangular footing only, because all my columns are rectangular, therefore I need rectangular footing. Now whenever we do the rectangular footing, so we usually take this as my length. Okay, usually we take this as my length. Okay, so this is my length, and this usually we take it as breadth. Okay, we take this as breadth. This is length, this is breadth, and we always try to maintain the ratio of length by breadth or breadth by length, length by breadth of 1.5 value. We always try to maintain the ratio of length by breadth 1.5 because that makes my footing more and more stable and more safer. Okay, so more and more stable and more safer, right? So that's the reason I always maintain my length to breadth ratio as 1.5. So based on that, so first we will find out the shorter dimension of the footing. The shorter dimension of the footing is represented by capital B. Okay, the shorter dimension of the footing, capital B. So that will be under square root of your approximate area of the footing divided by 1.5. Okay, the shorter dimension of the footing will be approximate area of the footing divided by the length by breadth ratio 1.5 under square root will give you shorter dimension of the footing. Okay, that will give you the shorter dimension of the footing, that is this one. I can say B. Okay, so in meter. So once I get the shorter dimension, you know longer dimension by shorter dimension we maintain 1.5. Therefore, if you want longer dimension, that is L, it is shorter dimension multiplied by 1.5. Okay, shorter dimension of the footing multiplied by 1.5 will give you the longer dimension of the footing L, that is again in meters. That is this one, that is L, capital L. So therefore, now we got the longer dimension of the footing capital L and the shorter dimension of the footing is capital B. So once your dimension is done, the next step is finding out the maximum pressure and the minimum pressure below the footing. Okay, finding out the maximum pressure and minimum pressure below the footing. Right, now your maximum pressure is represented by Q max and your minimum pressure is represented by Q minimum. Okay, your maximum pressure is represented by Q max and your minimum pressure is represented by Q minimum. So which is equal to your axial load. Okay, here you are not supposed to take the total load, you are supposed to take only the axial load divided by area of the footing, that is length into breadth, plus moment at the base, that is what you get from the software, that is moment at the base divided by Z. Okay, so Z is given by B d square by 6. Okay, Z is given by B d square by 6. So B is nothing but, you know, the shorter dimension of the footing. Okay, so D is nothing but, you can make it as L. So L is nothing but your longer dimension of the footing, that is B into L square by 6. That will give you maximum pressure in kilonewton per meter square. Then minimum pressure is also the same, that is axial load by the area of the footing, but here instead of plus you will be having minus moment at the base divided by Z. Z is again B L square by 6, that will give you kilonewton per meter square. It means what you have calculated is, you have calculated the pressure distribution below the footing. Okay, you have calculated the pressure distribution below the footing like this. This is what you calculated, the pressure distribution below the footing. This is what you find out, the pressure distribution below the footing. Right, so this will be your Q max, this will be your Q minimum. Okay, this will be your Q max, this will be your Q minimum. That is what we find out, pressure distribution. Okay, so when I made plus, I will get the maximum pressure. When I make minus, I will get the minimum pressure. That is Q max and Q minimum. Okay, Q max and Q minimum. So once the maximum pressure and minimum pressure is done, then you are supposed to write the shorter dimension of the column. Okay, shorter dimension of the column. The shorter dimension of the column is represented by small b, whereas the longer dimension of the column, shorter dimension of the footing is represented by capital B. And your shorter dimension of the column, it is an input value. So what we have considered in our modeling of the problem in the ETABS, that will be in meter. Then longer dimension of the column will be represented as small l, whereas the longer dimension of the footing will be represented as capital L. That is also an input value which will be given in the form of m. Right. So once this is done, then you are supposed to find out the critical section. Why you want to find out critical section? You are supposed to calculate the moment at the critical section. Okay, the moment at the critical section, right? So the moment at the critical section. So you are supposed to find out the critical section, right? So when you have an isolated footing with the eccentric loading, the critical section for the footing will always lie at the face of the column. Okay, this is your critical section for the footing, that is concentric isolated footing. Your critical section always lie at the face of the column. Your critical section always lie at the face of the column. Okay, this is your critical section. It lies at the face of the column. So now I have to find out this distance, right? So how I find out? That will be taken as small x. It is your longer dimension of the footing. Okay, your longer dimension of the footing, you can vary it from B to L or L to B. So therefore I am just writing in words, longer dimension of the footing minus longer dimension of the column divided by 2. That is this distance. If you are calculating this, then if I am taking this as L, then this is capital L minus small l divided by 2. If I am taking this as B, then capital B minus small b divided by 2. Therefore I can write longer dimension of the footing minus longer dimension of the column divided by 2 will give you the critical section x in meter. Once you calculate the critical section, then you are supposed to find out what is the moment at that critical section x. You are supposed to calculate what is the moment at that critical section x. So the next step is, we have calculated the bending moment at the critical section. Okay, we have calculated the bending moment at the critical section, right? We have calculated the bending moment at the critical section, right? So we have calculated here. So how we calculated the bending moment at the critical section? The bending moment at the critical section is equal to the maximum pressure, that is Q max. Okay, I have to take the maximum pressure Q max. Okay, so maximum pressure Q max multiplied by my longer dimension of the footing, that is length or breadth. How you take? Based on that I am telling longer dimension of the footing multiplied by the critical section x into again critical section x. 2 times you are supposed to do. Okay, so critical section x into critical section x will give you the bending moment at the critical section. Okay, bending moment at the critical section, right? Again I will tell you what I am doing. The bending moment at critical section is the maximum pressure Q max multiplied by the longer dimension of the footing, whether it is breadth or whether it is length, that is capital L or capital B, multiplied by 2 times the critical section. It is nothing but this portion, whatever I highlighted here, that acts as your cantilever projection, right? Whenever you have a cantilever projection with the UDL, how you calculate? For example, what I am telling is, this is my cantilever beam. Okay, this is my cantilever beam, and assume that on this you have an UDL acting like this. Okay, assume that you have an UDL acting like this, right? So when I want to find out the maximum bending moment, so what I will do, so let us know, you know that this is the length, so this is your value W, right? So it will be W into L acting at a distance of L by 2, right? So what will happen? It is W into L acting at a distance of L by 2, that is W into L acting at a distance of, because when I made W into L, it becomes a point load acting exactly at the center, into L, okay, by 2. That is nothing but your maximum bending moment at this support. So in the same manner, we are calculating the maximum bending moment at this critical section, that is Q max, that is pressure from the bottom, okay, into my total length of the footing, that is my dimension of the footing. What is my total length? That is B, okay, the dimension of the footing, that is B. So when I made that, so that will be converted to, it is your kilonewton acting at a distance of x into x by 2, okay, x into x divided by 2, same as that of your finding out the maximum bending moment at the support, right? This as well as this are same, that itself we have calculated, that is Q max into B into x by 2, that will give you the maximum bending moment at kilonewton meter, in the unit kilonewton meter. So then once it is done, you are supposed to find out the factored bending moment, okay, you are supposed to find out the factored bending moment. My factored bending moment will be 1.5 into my bending moment at the critical section, that will give you again factored bending moment in kilonewton meter, okay, it will give you in kilonewton meter. So once you know the factored bending moment, your next step is, you are, as you know, we have already find out the longer dimension of the footing as well as the shorter dimension of the footing. The next is, we are supposed to calculate the overall depth or the thickness of the footing. So with the help of this factored bending moment, we will calculate the effective thickness of the footing, which is represented as small d. The effective thickness of the footing or the effective depth of the footing, which is represented as small d, which is equal to under square root of factored bending moment into 10 power 6. When I multiplied this factored bending moment into 10 power 6, it will come in, which is in kilonewton meter, it will be converted to Newton mm divided by 0.138 into FCK into B. That will give you your effective thickness of the footing small d in mm. You may have the doubt that how I got this. When we go to the design of our beams, you know that based on the grade of concrete, we have bending moment is equal to 0.148 FCK BD square, 0.138 FCK BD square, 0.136 FCK BD square. We are using 0.148 FCK BD square when you have mild steel, that is 250 grade steel. 0.138 FCK BD square we are using when you have Fe415 grade steel. 0.136 FCK BD square it is done when you are using your Fe500 steel. So since I am using here Fe415 grade steel, I am using bending moment is equal to 0.138 FCK BD square. So when you simplify that, it is bending moment into 10 power 6 divided by 0.138 divided by FCK into 1000 under square root will give you D value in mm. So now for that effective thickness, you are supposed to add the effective cover. So when you add the effective cover to this, so you will get the overall thickness or the overall depth of the footing, which is represented in capital D. That will also be, it will be in mm. Okay, you will get the overall thickness or the overall depth, right? So that will also be in mm. Okay, yes. So usually as per IS 456-2000, for the footing you are supposed to maintain an effective cover of 50 mm because it is exposed in direct contact with the soil. Therefore you have to give an overall effective cover of 50 mm. Okay, just keep it in mind. So when I add effective cover to the effective depth, so you will get the total depth capital D in mm. Okay, you will get the capital D in mm. So once your capital D is found out, your next step is finding out the reinforcement details, because now you got the longer dimension, now you got the shorter dimension, and now you got the depth of the footing. Next step is how much reinforcements has to be provided, right? How much reinforcement has to be provided. Now, in order to find out your reinforcement, we will use one term called as percentage of steel. With the help of percentage of steel, we can find out the area of the steel, and from the area of the steel we can find out the spacing of the steel. Your percentage of steel will be found out from an chart, what we call it as SP16 chart. Okay, I'll just show you how the SP16 is present, right? So SP16, it is an design method for your reinforced concrete. Everything it will give you in the form of charts. Okay, this is an SP16. Right, this is an SP16. So this will give you the values like this. Okay, this will give you the values. Now, with the help of this SP16, we will find out your value of PT, that is percentage of steel, right? Yes. So these are your basics information. Yes, from here your tables is going to start. Okay, these are all charts. For the design of columns, for the design of footings, everywhere we will use this. Okay, yes, so this is not required now. Now, when I want to find out the percentage of steel for the footing, so I have to go to one chart called as, it will give you the value in form of mu by bd square. Okay, I'll just show you the graph. So these are the various graphs, not this one. Yeah, so this graph we are supposed to use, that is table 1, flexure reinforcement percentage PT for singly reinforced section, right? So here you can see that based on your grade of concrete, and it will be there on the grade of steel. So your grade of steel will be 240, 250, 415, 480, 500. Now this table 1 is for your FCK 15. Now, as we have already discussed, so for our problem we are choosing the grade of concrete for the footing and column is 25. Therefore I have to go to the table where FCK is 25. Okay, that is your table number 3. Now my F of Y is 415. Okay, that is HYSD bar. Now these values will give you the PT values, but in order to find out, we need the value of mu by bd square in Newton per mm square. Therefore, we have find out the value of mu by bd square value. So what is mu? Mu is nothing but your factored bending moment at the critical section divided by your shorter dimension of the footing, that is B, into 1000. Okay, so why I did this 1000 is because in order to convert your loading, your dimension which is in meter to mm into the overall depth square, because d square overall depth in mm, it should be squared. So when you do that, you will get one certain value. Okay, so that value you have to see here. Okay, these are the different values. So this value you can see here. If you are not getting the exact value what is there here, so then you can go for the interpolation. So that how to do, I'll explain you when I take up one loading on the column. So now generally I am explaining. So now let us assume that my mu by bd square value I am getting 0.60, and for this FCK 25 and F by 415 for 0.60 my value is 0.171. It means my percentage of steel PT will be 0.171%. right? But keep it in mind, student, as per IS 456 2000, for the footing, your percentage of steel should not go less than 0.12%. Okay, you can get from the SP16 chart, we will get the value of the percentage of steel required, that is PT. If when you found out that value, if your value is getting more than 0.12%, no issues. But if you are getting the PT value less than 0.12%, then you are not supposed to use that PT value, because as per IS 456 2000, the minimum percentage of steel that you have to maintain for the footing is 0.12%. If you are getting less than 0.12%, then consider the minimum percentage of steel 0.12% for your design. Okay, so once you get the PT value, then how to find out area of steel, and that thing we will see in the next lecture. Thank you, learners.